Can you conclude then that the data is more timely, it's more correlated over time than on space in this case?
Well, it's all a matter of scale, right? I mean, basically, it's saying that you know, you the if we were to look at where the variogram is less than 40, right? Maybe that's going to be the range, right? So the range in space is 125 kilometers. The range in time is 3 days, or 2 days. Okay, and so
as time goes on, then
so basically, it's, I mean, if you were to think of this as time as being another spatial dimension, that just tells you what the degree of anisotropy is between time and space, or between days and kilometers. So typically we want to construct a variogram that includes components. This is not necessarily a canonical variogram. This is just one example, and this is an example that's actually fit to a different data set than the one we just looked at. But the notion that there's a the variogram gamma has a component gamma naught, which is the nugget. Okay, there's a gamma p, which is for this model. Actually, there's the data that this model is fit to spans multiple years, so there's a seasonal component to the temporal autocorrelation. Okay, so gamma p is the periodic variogram, which has a period of 1 year. Gamma s is the aperiodic part of time. Gamma L is the spatial variogram, and in this case, there's no term that involves both space and time, right? And this particular model for this particular data set, they found that they could just separate, add up the spatial effects, the short-term temporal effects, and the seasonal temporal effects. And this is, so the nugget is just a constant. The periodic component is a cosine with a period of a year, and t is measured in days. And the reason that it's 1 minus a half the cosine is to ensure that the term in the brackets is positive. The short-term temporal correlation is modeled in this case as a spherical function. This is the equation for the spherical variogram, and where CS is, or sorry, AS is the range, and then the spatial component is just a linear function. The variogram increases linearly with distance. And here is just a
So
surface.
if we have some seasonality or periodicity, we need to actually account for that, plus the time temporal variogram, and then the spatial one. That is
right. So so all three of those things are in here. So here's what the actual variogram function looks like. And so here's the seasonal component. Here's the spatial component. So the variogram just increases linearly with space, and the sort of the extra shape you see it down here at short time delays of less than 100 days or so represents that short-term spatial autocorrelation. So you can see that the variogram last week's values are even better, even closer.
Is that plotted in R?
I don't know.
Or could it have been?
It could have been.
Yeah.
I mean, you can make plots like that in R. You can also make them in MATLAB and hopefully Mathematica. I didn't make this plot. um, so, uh, so how do you go about actually using these? You know, this was constructed just using in R, just using the standard variogram function from GStat that we used before. The data set had a somewhat different structure. It explicitly, you know, it was a different kind of data frame that was a spatiotemporal data frame, and GStat knew what to do with it. It took a long time. It took probably about 10 minutes to calculate this variogram. There were a lot of data points. But I'm still actually, I'm still sort of researching how you would actually use this. You know, conceptually, we can say, well, you would use this and you could do you know, a kriging. You could Krieg in space and time, right, using this variogram. So conceptually, there's nothing particularly difficult about that, but in terms of how you actually implement it in R, I'm still working that out. Likewise, conceptually, you should be able to take this and turn it into a correlation function to incorporate into the generalized least squares, right? So that if, for example, you're modeling NDVI across space and time, you can incorporate spatial correlations and temporal correlations in the model. And again, conceptually, there's no difficulty with doing that. The packages that actually implement this are a bit more specialized than I have. I'm still figuring out how they work, and whether we'll actually be able to make them operate over the next couple of weeks for you to play with or apply to your data sets.
In that example, would it still be a case of kind of looking at the ACF and PACF to estimate that part of the model?
Well, I mean, the ACF and the PACF would basically, I mean, the ACF would look sort of like this edge of the variogram flipped over on its head. So what you actually, what you actually do is more like the spatial analysis, where you construct the empirical variogram, kind of gaze at that, and remember with this simple variogram, we sort of had the empirical variogram, and then we said, well, what theoretical function seems to best fit that? Is it a spherical? Is it a Gaussian? Is it a linear? And then or exponential, and then move from there. I mean, that's the analogy of picking P and Q in the time series model. So in this case, you'd be simultaneously picking a model for the spatial component and a model for the temporal component, and potentially an interaction between them. And that's what this does. I mean, the time scale we were looking at doesn't have the periodic component, but it might well be that we would pick these two models for the spatial and the temporal variables. Actually, we probably wouldn't pick a linear model. We would pick something that was asymptotic. And then we would estimate these that model too. Um, well, so often what we're going to be interested in here is we're going to use a spatiotemporal variogram to make, I don't know actual map data, but to actually make, well, if we go back to here, right? If our goal is to, suppose we have kind of a coarse grid of samples in here, and we have a sample every 5 units in space and every 3 units in time. What we might want to do is we want to be able to interpolate in space at a given time. And the fact, and that spatiotemporal variogram allows us to use information from nearby times as well as nearby locations. So we extract information from the temporal dynamics as well as the spatial dynamics when we're making our interpolation, and we could just as well interpolate in time as well as space. So I will. I'll try to. I'll spend a bunch of time this weekend digging that up. The one other topic the one other new topic that we'll talk about on Tuesday is spectral analysis, and then for the final assignment, I've talked to some of you about other projects that we didn't do for this last one that might fit in. So Giuliano has a insurance claim data set that could be done as a spatial case control model. So that would be one project for the last homework assignment. It may well be that if I can get the sort of mechanics of the spatiotemporal analysis worked out, that Kelly's data and Hussein's data could be taken to that next step. And I think, Eric, you had...
Yeah, I'm not sure it's ready yet.
Okay.
Aaron's Herb River distributed temperature data.
Okay. And then you had a problem, didn't you? A fisheries problem?
Yeah, but it's still a problem.
Okay. So I will do my best to get the spatiotemporal mechanics working so that we can carry the two problems from last time into the next step.
I was looking at the data set I had, and actually there, on the attributes, there's the date of the claim for about 3,000 points, but that's the entire state of California. That might be too broad. So would it help to isolate that? Because I could start working on that. Would it help to make each claim an individual record on the data set rather than have one record with multiple dates on it? Would it help to transpose it, or too early to tell?
Think about that.
Okay.
Yeah.
I'll
Yeah.
talk then.
You can't transpose that way, just as an FYI.
Oh, it doesn't.
So you can't go from a single column with multiple data values to multiple columns. You can only go from-
Yeah, that's what I want to go from multiple columns to,
Oh, okay.
is that,
To a single column.
to single
Yeah.
column. Yeah.
You can't go the other way.
Yeah.
Not like it.
Sound like the
Yeah. Yeah, and there's ways to do that in R too. I think the command is stack or unstack.
Oh.
So in R you can actually go both ways. Okay, well enjoy your long weekend.
thanks.
Thank you. You too. I wish.
Oh, and I found another online textbook that sometimes there's analysis both on ARIMA models and spectral models that has some R code as well.
There are a bunch in